All right, welcome back to the sequel to my slides on depletion zones and diodes and field effect transistors. Today we'll be talking about Jfets. Up in the upper left corner you can see a schematic for Jfet, a junction field effect transistor, and an approximate schematic of what a Jfet might look like. There are all kinds of geometries and configurations for Jfets, but the basic idea is that you have a channel that connects the source to the drain, and then a gate which protrudes into the channel but does not go all the way. It does not cut it off. The name of the Jfet is determined by what the material of the channel is. So in this case, what you're looking at is a P channel, but we could also, and we will look at this in a few slides, also have an N channel where the channel is N material and the gate is made of P material. You will note that the channel and the gate make a PN junction, and so it looks sort of like a diode. And in keeping with following the schematic for how a diode works, you can imagine it looking like that, where the arrow, of course, points from the P material to the N material. And again, if you look at the schematic in the upper left corner, one of the important identifiers, or the important identifier of what kind of Jfet this is the direction of the arrow. And since the arrow is pointing away, we know that this is that there's a PN junction to the gate. The gate is on the N junction, and therefore this is a P channel. And that's how you can identify it. So the question is, how does this thing work? Well, the first thing is that, of course, because you have a continuous channel, you can flow current through it without obstruction. And so a Jfet, a field effect transistor in general, but specifically a junction field effect transistor, it's not necessarily like a bipolar transistor where your natural state is your off state. In fact, your natural state in this case is your on state. You can flow as much current as you are capable of in the on state, but then by varying the voltage on the gate, or specifically the voltage from the gate to the source, you can turn it off, and that's the action of this transistor. So now, as you remember from the last set of slides, where you have an NP junction, you of course have a depletion zone. Now I've drawn the depletion zone as this hazy green ring around the N-type gate material, but within that green band, of course, is the boundary between the N and the P. And if you remember, on the N side are positive ions, and on the P side are negative ions that are stuck on the lattice and that can't move. And those are what create the electric field. Now, if you remember from a diode, there's forward biasing, where you go in the correct direction, you follow the arrows, so you go from the P to the N, and then there's reverse biasing. And as you remember from the diode slides, when you reverse bias the PN junction, what you do is you grow the depletion zone. And that's the name of the game for Jfet, is you want to grow the depletion zone to the point where it completely chokes off the channel, and therefore you can no longer flow current through the P channel. So you start in the on state, and as you reverse bias the gate to source junction, the depletion zone is going to grow to the point where it's going to completely choke off the current. So this is a common configuration where you'll have the source at ground and the drain will be negative. Now, if you remember, what forward biasing is P is positive and therefore N is negative. So if we were to forward bias the gate, which will do nothing for us, we would apply a negative voltage. But of course, we want to apply a positive voltage, and that way the gate to source voltage, the gate will be more positive than the source, and that's going to reverse bias this junction, and it's going to grow the depletion zone. This shows the flow of current. Of course, that's opposite the direction of the flow of electrons. Electrons are going from negative to positive, but the conventional current, which is positive, the flow of positive charge, goes from the source to the drain. And it's that corridor there that the yellow arrow is going through that we want to choke off. So how do we bias the gate? Well, again, reverse bias. Instead of n being negative, we want to make n positive, which means we want to make the gate positive. And if you think about that imaginary diode there, again, you're reverse biasing that diode. That means we make the gate positive, and what happens? Boom, boom, boom. The depletion zone grows, and it chokes off the diode, and now current can no longer go from the source to the drain. Now, I will point out that this is a cartoon depiction. You'll notice that in my cartoon depiction, the depletion zone grew symmetrically around the gate, but that's not really true because the reverse bias is largely between the gate and the source. But in any case, there is this growing depletion zone, and that's going to choke things off. I should also point out that the source in this picture is ground, but even if the source is positive, that's okay as long as the gate is more positive. The key thing is that we're reverse biasing, and the voltage that we refer to when we're thinking about reverse biasing is VGS. So VGS needs to be positive for a p-channel Jfet in order because the gate is N material, in order to grow the depletion zone and block current. VGS needs to be positive. Just to show you guys an N channel, so with an N channel now, the gate is a P material. That means that if I were to think about the direction of the direction of the diode is now pointing from gate to source. If we were to forward bias, P would be positive, but of course the whole point is we want to reverse bias. So for an N channel, the gate needs, the drain in this case will make positive, the source is ground, the gate needs to be negative, that grows the depletion region, and it blocks off the current, and so VGS needs to be negative to turn off current, and as I drew here, two negative signs for the gate and one for the source, it's okay if the source is negative as long as the gate is more negative. So to recap, an N-channel Jfet has a P-channel gate, and therefore the gate to channel is like the PN of a diode, and so the arrow on the schematic is pointing inward, as you can see in the upper left schematic, and VGS needs to be negative because that reverse biases the PN junction, and VGS again stands for voltage gate to source. That's showing the P and the N. This is a plot of the transconductance curve, and so you can see that you start out with the largest possible current when VGS is at 0, and then as you make VGS more and more negative, the current goes down. The upper left or the upper right corner shows you as a function of V from drain to source. As you ramp up the drain to source voltage, you get to a region that you call the steady state current. But for different GSs, you can see for VGS equals 0, your steady state current IDSS is as high as it can be as you increase VGS in the negative direction, making it -1 volt, -2 volts, -3 volts, etc. That IDSS goes down until you get to the cutoff where you choke it off. And so the red plot, that red curve, is just showing the value of the steady state current for each of the VGSs. Here's a picture sort of on that curve of what's going on. The topmost picture of the transistor has no voltage applied to the gate, and then as we're applying more and more voltage, we're choking off the N channel more and more to the point where no more current can flow through. And similarly for a P channel, VGS needs to be positive to turn the current off, and you can see that the steady state current as a function of the gate voltage goes down, and that's it.